All right, hello everyone, and welcome to the second synthesis section of POPL this year. So I think I can confidently state that not only are the titles and the introductions of all these papers exciting, the actual technical content is too. So get excited for our talks. So our first speaker today is David Cal. He's going to be talking about a really exciting approach of using E-Graphs to accelerate library learning. And I'll really quickly note that David is senior undergraduate student. Look out for his application in your portal. These students.
Cool. Can y'all hear me in the back? Very slay. Okay. Hey y'all, my name is David, and for the past little while, I've had the privilege of working with these wonderful folks on Babble, which is a new approach for more robust library learning. So before I dive into technical bits, I want to give you all a motivating example for this problem. So, imagine you're doing some programming. For this example, we're using a graphical DSL consisting of scales and translations of unit circles and unit length horizontal lines, just because it makes the examples visually clearer. And let's say you're looking at these two programs here. Now, just looking at the visual output of these programs, it's pretty obvious that they share some common structure. In particular, they're both faces, where the mouth is a horizontally stretched out version of the eyes. Both of them contain a uniformly scaled circle representing the outside of the face. Both contain some shape that's translated to get our two eyes. On the left, we use the unit circle, and on the right, we use a line that we rotate first. And both contain that shape horizontally stretched and shifted to get our mouth. So there's some shared structure here, and if we were writing the code ourselves, we might want to extract this common behavior out into its own face function that we can reuse later. And we can do just that. Here's a function parameterized over some shape that gives you back faces where the mouth is a stretched out version of the eyes. Of course, this face function has our little outer face component and the stretched out shape for the mouth, but it also rotates its eyes. We do this since we need to rotate the line input's eyes, and we can rotate the circle input's eyes without changing the output image. But details aside, the upshot here is that when we program and when we want to reduce code size and increase code reuse, we look at common structure in our programs and abstract it out into their own functions. And beyond graphics, DSLs, and smiley faces, this is something that humans are really good at. Indeed, normally when we program, we're not putting all of our code into one big main function, right? Instead, we're constantly looking at shared structure in our programs and finding places where we can abstract out functions that we can reuse across our programs. But what if we could get computers to do this abstraction step? What if computers could look at a bunch of programs, see where they share a common structure, and give you back functions that can be reused across your input corpus of programs? This is the problem of library learning. The computer is given an input corpus of programs, and it gives you back a list of common abstractions that can be used to re-express our original programs. Now, which abstractions are the best are a somewhat subjective metric. So taking from other work in this area, we define our evaluation metric to be best compression. In other words, we want to minimize the total size of our abstractions and programs, and Babble is the tool that we've created to tackle this problem. Now, before we move on, you might be asking yourself, who cares about this problem? The reason I just alluded to was code compression, making your code as small as possible. But there are a bunch of other uses too. Maybe you're trying to design an FPGA, and you want to figure out which operations to optimize for or devote dedicated hardware to. You can throw in some example FPGA programs into a library learning tool to see which functions are used the most and will give you the most bang for your buck. Or if you have a program synthesis procedure which builds its programs from some DSL, you can run it on some tasks, run library learning on the output programs to get a new set of good abstractions, then add those abstractions back into your DSL to make even more complex programs. And this is some very cool work done by some MIT folks here called Dreamcoder. Or maybe you're a cognitive scientist and you're trying to figure out, if humans can do how humans can do this common structure recognition. Well, if you can make a computer do it, that might give you a sense of how humans can do it too. So the bottom line is this is a really useful problem that has a bunch of general use. So with that in mind, the rest of this talk is going to have 3 parts. First, we'll talk about why this problem is hard and why Babble needs to exist in the first place. Then I'll give you all a taste of how Babble works before going through some evaluation results. Starting with the challenge that we want Babble to tackle. So in general, there are a bunch of different challenges and complexities that a practical library learning system needs to be able to address. For example, it needs to be fast and scalable. In the real world, we have much bigger programs situated in large code bases, so our approach needs to scale well. We want to be able to learn abstractions and subterms, not just abstractions that can only be applied at the top level, like with our examples here. And we want to be able to handle nested abstractions so that we can learn common structure within our abstractions themselves. And to a large extent, both Babble and other work have addressed these problems in some capacity. But Babble focuses on tackling a different challenge, incorporating semantic equivalence. And to explain what I mean by this, we're going to go back to our faces from before. So for a second, let's pretend that we're the computer. We don't know anything about circles or lines or geometry, and we're just looking at these programs purely syntactically. Well, it would seem like the best we can do is learn an abstraction that takes 2 arguments. First, we need an argument for eye shape. It's circle on the left, rotate 90 line, on the right. Second, you need an argument for the mouth shape, circle on the left, line on the right. Thus, the resulting abstraction you'd learn would look something like this. 2 argument abstraction, 1 for eye shape and 1 for mouth shape. And if you'll notice, this is a slightly different function compared to the one that I was presenting from the beginning. This abstraction isn't a face where the mouth is a stretched out eye. It's just a face. So for one, this abstraction failed to represent and reproduce one of the defining features of our data set. More importantly, as we defined in our problem earlier, we want to minimize code size and maximize code compression. And while this abstraction might be more compact if we only have 2 of these faces, if you have 200 or 2 million faces, the face-ish abstraction fails to scale as well, since each invocation requires more code. And so the main issue here is this highlighted term. In the second input, we need to rotate our line by 90 degrees in order to get our desired eye shape. But in the first input, since circles look the same regardless of rotation, we don't have that rotate term in our program. There's no more shared syntactic structure here, and we're forced to introduce a new function parameter. So how are we able to recognize this common structure? Well, we know that if we were to add those eye rotations into the original circle input and rotate our eyes, the program would be semantically equivalent. In other words, it would behave the same. Rotating a circle doesn't do anything, and since this second equivalent version of our program shares that common structure with the second input, we know that we can use that common structure for both of our inputs. So our challenge is, how can we make computers do this? Can we make a library learning algorithm that can discover more precise structure by considering how semantically equivalent versions of our inputs can share structure? Well, the answer is yes. And in this next section, I'm going to walk through how Babble tackles this problem. So mainly, the key idea here is that we want to consider multiple semantically equivalent versions of our inputs. In particular, since we don't know which form of our program will yield the best sharing across our corpus, we need to consider every possible equivalent version of our inputs. These versions may be more complex locally, but across the whole corpus, they may introduce more common structure. So this now begs the question, how do we know what's semantically equivalent? Well, we can modify our problem statement a little bit. Before, the only input that the user passed in was a corpus of programs to perform library learning on. But now we also ask the user to provide an additional input, a list of equivalences that tell the computer how terms can be rewritten, that codify intuitions and symmetries like circles are rotationally symmetric and scaling an image by 1 results in the same image. This reframing of the problem is our first contribution, and we call it library learning modulo theory, or LLMT for short. Now, having to consider an infinite array of programs might seem impractical, but Babble has a few tricks up its sleeve to make this tractable in practice. First, we make an insight that we can use equivalence graphs, a data structure from literature, to create and store all of our infinite equivalent input variants efficiently. Second, we create an algorithm called E-Graph anti-unification for proposing candidate abstractions in the presence of E-graphs. And finally, we create an algorithm called targeted common subexpression elimination, or targeted CSE, which lets us pick the best versions of our programs and abstractions. This is Babble's secret sauce, and we're going to spend the rest of this technical section giving you all a flavor for how these things work. With the caveat that since we're limited on time, we won't be covering the last contribution in too much detail, but it's very cool, and if you want to know more about it, you should check out our paper. In any case, we're going to start with E-graphs. So just to recap where we're at, our problem was that if 2 expressions don't syntactically align, a computer will have no way to find the best possible abstraction, even if we humans can recognize there's a better one available. We realized that if a user could tell the computer what's equivalent to what, the computer could use those equivalences to generate every possible version of our inputs, including versions which locally might look more complicated, and eventually generate and find the best versions of our input programs that'll give us the most shared common structure. Well, we now have a new problem. Which version of our programs do we use and keep in memory? Or in other words, when do we stop rewriting? If I wanted to, I could keep applying my scale identity over and over and over again, and if nobody stops me, I can generate an infinite amount of these programs. And we don't know beforehand which of these versions generates the most sharing. It could be after 1 iteration or after 1,000. So how do we know which of these versions to use? So to solve this issue, we use a data structure called an equivalence graph, or an E-graph for short, to compactly represent sets of equivalent programs. And you can think of an E-graph kind of like a superpowered abstract syntax tree. Indeed, this E-graph, which represents the term scale 1 circle, is literally just the AST for that term, with the exception being that we use the term E-node to refer to the AST nodes in this term. However, E-graphs are different in that they can contain equivalence classes, or E-classes for short, which record which E-nodes are semantically equivalent to each other. Additionally, each child of a particular E-node is an E-class, which means that they can refer to themselves. Thus, we can represent infinitely many programs with this compact data structure. The nice thing about E-graphs is that they have a built-in operation to take in the list of equivalences that a user has passed in and update the E-graph to add terms where needed to reflect the new set of equivalent terms represented. This operation ideally continues until fixed point, but can be time or space bounded if needed. And of course, the resulting E-graph takes finite space instead of having to store like an infinite array of different programs. So we can now create and store a bunch of these equivalent versions of our inputs. But how do we actually come up with candidate abstractions at this point? Well, that's what our second contribution, E-Graph Anti-unification, is for. So yeah, we're now dealing with an E-graph of programs, which could contain potentially infinitely many concrete terms. Because of that, we need to be more efficient and more picky in how we suggest candidate abstractions. And in particular, we want our abstractions to abide by two main criteria. First, our abstraction should be usable in multiple places. So for example, I have some simplified inputs on the side here, and learning the abstraction scale for x wouldn't work since it only occurs one time in the E-graph. There's no point in learning a library that you can only use once in your entire corpus. Second, we want to maximize the shared structure that our abstraction can abstract away. So for example, with rotate 90x, this is a reasonable function to learn for our inputs. However, we don't want to just stop there. We could also learn rotate 90 followed by scale, x and y. And if you remember with our faces, one problem that we had is that the abstraction we learned wasn't specific enough. It wasn't capturing all the shared structure that we observed in our data set. So our algorithm needs to also be able to learn as specific and concrete an abstraction as possible. So in literature, there's an algorithm for finding the most common structure between two terms called anti-unification, which can find common structure with a top-down approach. Basically, you start at the top of both terms. You check if both nodes are the same. In this case, we have two rotates at the top, which are the same. Because of that, we add the node to our current pattern and recurse into its children. Same applies to the first child. Both are this 90 term here, so we add it to our pattern. And since it has no children, we go to the other sibling node. Same applies here, but this time we recurse since it has its own children. Now for the first child, since the nodes are different, we insert a hole where a fresh function argument will eventually go. Same for the second child. And that's it. We're done. We have a pattern that we have derived algorithmically from our two different inputs. Now our challenge is to somehow apply this algorithm to work with E-graphs. So we did just that and made an algorithm that adapts anti-unification to work in the presence of E-graphs. And I'll quickly run through this example to give you a sort of feel for how this works. But basically, the first step is picking two E-classes in the E-graph since we need somewhere to start. From here, the steps we follow are pretty similar to regular term anti-unification. If the two E-classes selected contain matching E-nodes, which they do, we run step 2 again with the matching E-nodes children. In this case, they both contain a rotate, so we add rotate to our pattern. Now, if two E-classes contain multiple matching E-nodes, we might end up with multiple output patterns since we have to run this step on each of those pairs. But for this example, it works out that we only have one output pattern. So recursing into the first shell again, we have 90. The E-classes contain matching E-nodes since we're pointing to the same E-class, so we can add this to our pattern. Same applies to the other child. Both contain a scale. We recurse into the children. Now, when examining the first child, the E-classes here don't contain matching E-nodes, so we insert a hole for the first function argument. Same for the second child. We insert another hole there, yielding our complete pattern for this particular pair. And to complete the cycle, we just run this procedure for all pairs of E-classes in the E-graph. So that's a very, very simplified version of our complete algorithm for E-graph anti-unification. In practice, we make quite a few changes to make this more practical. So for instance, we use dynamic programming to make sure we're not constantly recalculating anti-unification results. We also don't just randomly pick two E-classes when we start. We have a smarter way of going about this. But this should give you a rough flavor for how this process works. And again, if you want more details, you can check out the paper. Our targeted CSE algorithm tackles the other part of this task, candidate abstraction selection, how we find the best possible subset of libraries to use, along with the versions of our original input programs to use in the presence of an E-graph. But again, since we're short on time, more details can be found in the paper. So how well does this work in practice? Well, on the right here, I have listed an input file containing 250 different programs. And while I explain what's going on here, I'm going to let Babble run in the background. So we tested Babble on two data sets, the library learning data set from Dreamcoder, the program synthesis tool I alluded to earlier, which contains a library learning component, and another library learning benchmark data set from prior literature. This right here is a set of input programs from the latter data set containing a bunch of drawings of nuts and bolts. And these programs aren't trivial either. As you can see, each of these programs by themselves is pretty complex, containing a bunch of nested terms and a lot of opportunities for learning shared structure. And if you try running Dreamcoder, the prior state-of-the-art in library learning, on this problem, it'll spin for hours and hours and still won't finish learning a single abstraction. But with Babble, in the time that it's taken for me to explain what's going on here, it's finished learning and learned 5 abstractions. And from the stats that it's showing right now, it's managed to compress this data set by over 4 times. Additionally, the abstractions that Babble can learn from this example actually make sense. I've highlighted a few of the functions we learn here. We can learn concentric hexagons, a ring of shapes, and a scaled n-gon, which map well to distinct visual concepts that a person like y'all or me might recognize from these examples. And in general, looking qualitatively, Babble's pretty good at recognizing these distinct concepts that you or I might identify. Here's an example I just took straight from the paper. If you give Babble a bunch of programs representing shelves and other furniture, Babble can recognize and reuse an abstraction for an individual shelf. And of course, if you want the full qualitative evaluation, we show more visual examples of what Babel can learn in our paper. Now, for a more quantitative evaluation, we also evaluated how Babel performs against Dreamcoder on its own data set. We have two evaluation metrics here. How well do we compress? In other words, do the E-graph magic and the modulo theory part of library learning modulo theory make any difference? And how fast do we compress? In other words, does our E-graph anti-unification and targeted CSE algorithms work to make library learning feasible with E-graphs? This graph right here contains metrics for both. The x-axis represents compression ratio. How many times smaller is Babel's output compared to its input? While the y-axis represents speed. How long does it take to finish? And you may notice that the y-axis is on a log scale. Keep that in mind for later. In general, down to the right is where we want our results to tend towards. This means big compression, small time. So to explain what's happening here, I'll give you all a brief rundown of how the Dreamcoder dataset is set up. This dataset is divided into multiple domains. So each domain represents a particular language or type of program. So there's a domain for logo programs, a domain for text manipulation programs. In this case, we're looking at results for the physics domain, which basically contains a bunch of mathematical formulas. Within each domain, there are multiple benchmark files corresponding to multiple sets of programs. Each dot here represents running Dreamcoder on one set of those input programs. In this case, the most compressive set of programs achieved a near 1.2 compression ratio after running Dreamcoder's library learning procedure. As you can see, most of the results are sort of clustered closer to the 1.0 mark, and these results take between 100 and upwards of 1,000 seconds to finish. So what if we just use E-graph anti-unification without library learning modulo theory? In other words, what if we just throw everything into an E-graph, ignore a list of equivalences, and just use anti-unification and targeted CSE on that? Well, our results are already starting to look a little better. We're running significantly faster by a couple of orders of magnitude for the most part. But more importantly, we're also getting better compression. We're reaching compression ratios of 1.2 to 1.6 for the most part. But this still doesn't include our equivalences. So what happens if we turn on all of Babel's dials? Well, not only do we get pretty good performance that still exceeds Dreamcoder's by some orders of magnitude still, but we also get massively improved compression. We're approaching compression ratios of 2.6 here. There's a similar story for the list domain, which contains programs using list operations like fold, map, and filter. Dreamcoder's results are all clustered in the top left here. And if we ignore our equivalences and just do anti-unification, we can get pretty solid improvements in performance and compression. Again, performance improves by a few orders of magnitude, and we see a solid improvement across the board in compression ratio, with the best compressing data set having a ratio around 1.3. And again, if we turn on all the dials, we still get great performance and see largely improved compression. The center of this clump of dots has moved towards a compression ratio of around 1.15, and our most compressed data set is seeing a compression ratio of over 1.45, which is a pretty significant improvement. And again, our paper has more results showing all of our quantitative results, but the upshot is not only do we learn functions which make sense and correspond well to distinct concepts and structure we would recognize, but we also compress and scale well compared to the prior state of the art. So with that, thank you all so much for y'all's time, and I'm happy to take any questions that y'all might have.
Okay, we have plenty of time for questions. I'd just like to remind people to please state your name and affiliation before asking your question.
Hi, I'm Sam Westrick from Carnegie Mellon University. You showed optimizing for compression, but you could also optimize for other things like performance. And is that something you've considered, and is it feasible? Do you think it would be effective?
Yeah, so the question was, can we optimize for other evaluation metrics? In theory, yes, it's possible. In practice, we just use compression since it's the easiest to measure. You just count up the AST nodes. And prior work has measured library learning performance in terms of compression, so that's just what we use. But in theory, there's nothing stopping us from evaluating based on performance or another metric like that.
Any other questions? We have one in the back.
Hi. Yeah. Elijah Rivera, PhD student at Brown. You mentioned at the beginning of your talk, essentially, if we could, like, this might help tell us something about, like, how we as humans figure out this abstraction stuff. Do you have any even, like, speculation on what your results actually tell us about that?
So we didn't examine that too much for the purposes of our presentation. Again, like when we're operating in the library domain or the library learning domain, we're just sort of looking at how to maximize code compression. So that's definitely something that future work and something more in the cogsci domain can answer to be particular, but we don't have too many answers about that with our work here.
Hey, do we have any other questions? Oh, multiple.
Gregory Blake at UMass Boston, and I was wondering, with the compression metric, do you have any sense for how far this is compressing these programs towards any sense of limit?
Sorry, could you repeat the question?
Oh, is there? Do you have any insight for what is the limit of the compression via this strategy?
The limit of compression? So the question was if there's like a limit to how much compression we can get out of this technique. Obviously, you can only go so far, right? The best you can perform is you have one abstraction that you reuse for every single program in your corpus. So that would be like the theoretical, like best case, like you have an exact, like ideal scenario where you have a bunch of shared structure. If that answers your question. Yeah.
Do we have? I think we have time for one more question back here.
Hi, Rafael Lozana from University of Rochester. What is the format of the list of equivalences that you give? So for instance, you have circles, rotate 90-degree circle there, but technically it could hold for any value, not just 90. So how would you incorporate ideas like that of more complex equivalences?
For sure. So there's a little example here. The syntax would basically be you specify like a hole, and you can say a rotation by any term there will still result in an equivalent circle. So with this like scale identity, for example, we're saying like any shape, if you scale it by 1, will still result in the same shape. For circles, you can do something similar to that. Instead of saying circles equivalent to rotate 90 circle, you'd say like, oh, rotate some amount circle is equivalent to circles. For the sake of simplicity, I've just displayed the version with 90 degrees, but in theory, you could add a hole there, and then that would account for all the rotational symmetries of circles.
Okay, great. Let's thank David again.